I'm going to try to continue with what we've been talking about, but I'm going to kind of go backwards a little bit. I have looked at most of the stuff that was in chapter 1 of your book, and even if you've been proceeding in the class, what this is just something to give as an additional reference you can take a look at. One of the things that I want to try to do is I don't want you to just like memorize things or just get a basic understanding about what's not happening under the hood. And I also don't want to start using terms and you not knowing where they're from. So, and I'm also going to not make assumptions that you know all these things. I mean, I know you've grown up with computers and things like that, but you might not have looked a whole lot at the insides. And so I kind of want to talk a little bit about that. So today we're just gonna chat a little bit more about what I think is in chapter 1 from what I read. I'm going to talk a little bit more about objects. The book doesn't, but it's part of my thing of just saying is that I hate using the word objects. You're going to see it in the code and saying, well, just type this in and trust me. I'm not going to go deep in it, but I do want to give you some understanding of where we're headed. And then once we talk about objects kind of as a concept, not just as it is in Java, we're going to talk about it as a concept, and then and I'm going to give you some historical context of where computer science was to kind of get to objects. What was the driving force? What was their motivation for going to this paradigm? And then a little bit more about Java. So I'm going to stop here for just 1 second because I want to make sure this is recording. I'm doing this kind of on a kludgy system. I do apologize for a lot of things. I've had some unexpected travel. Right now I am doing this while I'm in New York City. My schedule will settle down soon. This was really unexpected. And then I will be, especially after January, I'll be a little bit more settled. Although I have some travel there, but that's a little bit different travel. All right, I'll be back in a second. Okay, things seem to be working, at least I hope. All right, so I'm going to briefly go through what is going on inside of a computer. I'm not going to go into a lot of detail, but I just kind of want to begin, a little bit of the conversation about the hardware. We're going to spend primarily our focus on software. But the software has to run on something, and the software is designed such to support or work with the hardware. It doesn't go against it, it actually works with it. So a lot of the behavior of things that you will see have been optimized in the software because of how the hardware works. So the world kind of starts from like a left to right kind of a thing. Here's all the things on the outside that you're familiar with: keyboards, a mouse. Other input might be a microphone like I'm talking to now, a video camera, things like that, Ethernet cable, all those things will come in this way. That's where the internet comes in, for those that don't know what an Ethernet cable is. In here it'll come into memory. It actually goes into memory and it writes into a special part of memory. And we're going to talk about memory because memory is kind of an important thing. The word RAM here is random access memory. Which is a special type of memory. But the data comes in here. This CPU, the central processor unit, is kind of the active agent in this whole thing. When this thing is running, it basically is looking at memory, reading instructions, and doing some work. Okay, so it reads in memory some type of program that you guys put together, or Microsoft put together, or someone put together, that it gets from memory, brings it inside of the CPU, and it says, okay, those are the instructions, this is what I'm going to do, and then it's going to do the work. Now, part of that work may be writing to the hard drive. That's what HDD stands for. It's the hard drive. You can tell it's a bit of an old picture. There's a CD. Nowadays it'd be a Blu-ray or a DVD at least, to grab more data or to write data, right? So you can store information that you had collected. You can put it on the hard drive, or you can write it out to the optical drive here. But I want you to notice something here is that everything goes through memory. Everything, this is a very key juncture point in how the basic architecture works. The CPU works with the data in memory. Anything that I want to get stored out into more persistent memory, because like once you shut off the power to your computer, whatever's stored in this memory is gone. But what is left on your physical hard drive, or SSDD nowadays, is kept here even when the power is off. Same with the CD. Another part is that stuff goes out. So you're familiar with your monitor. So data comes out through the memory, goes into your video card. There may be some more electronics in here, but this is just a very simple example. And then it goes to your monitor, to the printer, to audio speakers, or out to the internet, right? That could also be here too. So you have this basic flow from input device through the machine to an output device. And internally, the CPU looks at program instructions that are stored in memory and activates and activates. It acts on whatever it's told to do. Again, remember what I told you. Computers are dumb. It's only doing what it's instructed. It's just a machine. Okay, well, all of a sudden he goes from that to binary. Well, there's a reason, because we're going to talk a little bit about it, and I'm hoping this is a refresher. If it's not, we can discuss more about this. Your teacher can maybe deal more with this too if she wants to. But binary is kind of the language of the hardware of computers. It's at the lowest level. It's only made up of, in case, I'm assuming most of you know this, but I'm just going to say it because I don't know for sure. But binaries are just ones and zeros, whereas like with base 10s, you have everything from 0 to 9. Computers make great use of the binary numbers because it's off and on. That is the trick. In other words, something's on, something's off. If you decide to go down more into computer science, and we will touch on this a little bit in the class, but you're going to do something called Boolean logic. Boolean logic is a bunch of ands, ors, and all sorts of really neat things that when you put them together, they create these logic sequence that makes things happen. But we will talk more about that, but just think of it as like left to right. There's no gray. It's either on or it's off. Now, the reason why I brought this up is because of the next slide, and it's that last bullet. Boolean addressing is how we address things in memory. Because you use Java, you don't see this. And this is why, this is one of those things a little bit under the hood. I wanted to explain to you what's happening on the computer side, because Java does not get into this that much. Programming languages like C, for example, and even C++, there is some dependency. There's more dependency on you understanding how the underlying hardware worked, because that is, in a lot of ways, how older systems worked. And I just wanted you to get some feeling for it. In the Java language, you're not going to have to get to this level of detail, but I think it's good to know. So anyway, over on this side of the screen are some examples. And so, first off, what they do is they represent each of these binary digits that are here. Each of the place that they're located at is a weighted function. So it's 2 to the 0. So this could, if this was just if you get rid of all these and you just had a 0 here, right, like this one here, these are all zeros, then it means a decimal equivalent of 0. You put a 1 there, it becomes a 1. The second digit, with that one being 0, gives you a 2, 3, 4, 5, 6, and then finally 7. And that's pretty much how that part works. It's really not that hard, but it is a different way of looking at numbers. And as I said, inside of the computer, this is how it works. It's really just doing it at this level of math. Okay, the reason I brought it up was because of this is how memory is set up inside of your machine. So going back to this picture here, this part here, all right, so when you write a program, all of your program instructions are going to be stored in sequential memory locations in memory. Okay, so let's think about when you run a program and you run Chrome, or you run Internet Explorer, or you run a video game, or you run something like that, and you have so much memory in your system. Okay, if you only have 4 gigs of memory or only 8 gigs of memory, you can only run so many applications before the system says, I can't run anymore. I can't fit any more programs in here. There's something called virtual memory, which uses a little bit of the hard drive to kind of make up for that. But just think about it. Anytime you go out and do something with the hard drive, things get slower. So typically, most systems, you want to keep all of your applications in here. All right, so everything here is sequentially. Why is this going to be important? We're going to come back to this slide later on, because we're going to do things with things called stacks and linked lists and all sorts of other data structures, if statements, do loops, and stuff like that. And what I'm going to do is when we start talking about that, I'm going to show you what it's actually doing inside of memory here, just a little bit, just so that you'll understand what's happening. Because when you have problems with things, or when things don't work correctly, if you understand what's underlying under the hood a little bit, you will say, okay, I know why this isn't working, because I have a memory leak, or I'm trying to do things in an incorrect fashion that the hardware can't support. I need to rethink what I'm doing. But anyway, when we start working with this, we'll find out we just put all the data will go in sequential address spaces. All your programs will be here. And as I said, we'll come back to this later. The other thing that's interesting here too is when we start talking about data types, I'm going to show you in memory how things get allocated in memory for different types of data. Just give you a quick instance, like think of integers, which only store data from negative to positive whole numbers. But then think about how double, like real numbers like 10.162 or negative 13 to the 11th power or something like that. Well, how do I store that? How does that information? Well, we'll find out that gets stored differently here in memory. So when we start talking about those data types, we're going to come back to this picture or a similar picture and discuss how these things are done. It's not so much that's part of the test, but it's really more just to deepen your understanding so that you will appreciate some of the other things, like why is this taking up so much memory? Why does this behave a little bit differently? Why does the computations on this different than that? And you'll start to understand it's like, oh, because if I read things from memory, if I'm trying to read a real number from memory, but I'm only using an integer, well, the machine says, I don't know how to do that, because it can't. It's stored differently in here. So we're going to talk about stuff like that. But again, a little bit down the road, I just wanted to start introducing the topic a little bit. I also want to show you what a computer motherboard look like. Some of you may have not popped open your computer before. Some of you have been maybe told not to pop open your computer before. And I'm going to do a quick tour. If there's interest down the road, I actually, as a hobby, I do a lot of things with water cooling and playing around with computers. I've built several over the years, and it's a lot of fun. It can be a little bit of an expensive hobby, but it can be fun. What I want to do is I'm just going to show you the main things here. So this is a typical motherboard, okay? And this piece right here is where the CPU is going to live. And this is the underside of the CPU. And you see all these little pins? All these little pins are going to have to make contact with something down here to make it work. So you actually take this CPU, you place it inside of this squared area here, and then this thing right here, I don't know what it's called actually, but you close it down onto it, and then with this lever you lock it. And that's how you install a CPU. I can probably come up with a video of that one time. But that is where the CPU lives. It lives right there on the board, right here, right here. Okay, now on this side, when we talked about the I/O, well, over here is all your Ethernet connectors, USB connectors, whatever you want, video, all that stuff lays on this part of the board. Okay, here's your CPU. These are your memory cards right here. These are all those slots for them. This is a memory. This is a stick, a memory stick. You take this part here, you see these little metal pieces here, and you slide them right into here, and then you lock them down here. So there's your memory. So your CPU is talking to your memory right there. And here's on the other side, here's the I/O, which all through the circuitry here is getting its data to do that. This blue thing right here is your power. It's there's two power. This is where you would plug in your power supplies here and here. Down over here are your SATA connectors. This is a rather old picture. I should have looked for something newer. But these are SATA. This is how you talk to your hard drives or to your SSDD. These are all you see the little unique kind of slot. You need a special cable to put in there, and then that cable goes to your hard drive. Oops, sorry, I clicked it. Over here is your USB headers. Now, on the back of your computer, you often have USB connectors, but then sometimes on the front case you have USB connections. These are some ribbon cables that you put, and then you wire it up into your onto the front panel. There's also this in this part here, I think, or at least commonly it's in this area, are things for like your on-off switch, so that you can control the power going into this board. You can turn it on and off. And then this here, these are PCI slots. This is where you slide in your graphics card. And then it would fit out towards the back over here. Okay, so here's where your graphics card would lay in there. I should have gave a picture of that, but we'll do more on this later. But this is physically the basic arrangement. This is what's inside. Oh, the fan stuff over here. There's little pins. These things right here. Typically, when you turn on the computer, heat is a real problem with these guys. You have to get heat out of the box. And these connectors here just go to the fans that are connected to the cabinet of your computer. So CPU, memory, all the I/O, all the USB and all that kind of stuff, Ethernet. Then over here, your SATA cables going to your hard drives, power. Here is your I/O connectors to your front control panel. Your USB, they call them headers. They're just cables that would go off and talk to that. There also may be something in here for sound, so you can get a sound connector going up so you can put your headset into your computer. So that's, sorry about that, I've done that twice now. This is very sensitive, I guess. All right, so let's move on to objects. Everyone gets in objects. It's a technology that when, as a concept, it was in response to problems we were having with software development. So this is not something that was just like came up. It was actually an evolutionary process. So I'm going to start this by telling you some stories, because I think if you understand where something came from and what was the motivation for doing something, then it may make you appreciate why you were doing it. So in other words, instead of just like trying to teach you about objects, I want to teach you like why we got to objects and why they are right now a much superior way than what we were doing. So you are coming in late to computer science. A lot has been going on over the last 50 to 60 years, but the truth is computer science goes even further back than 50 or 60 years if you really want to get into it. That there is the ACM, which the Computing Machine Association, ACM, Association of Computing Machines, because technically, if you think of clocks and many types of computing machines that go back to the Chinese, and several people go back several, I want to say hundreds, if not longer, of years that they were developing computing machines. What makes these machines that we're doing different is that they were electrical, and they got smaller, and so we've kind of make it look like it's new. But the truth is, many of the concepts and many of the math and many of the things that are involved with it are not new. The idea has been around for a long time. So, like that third bullet, you guys weren't around for the real bad old days of software. We used to have things literally like wizard programmers, and code was no good if it wasn't built here, and there was even a contest called Obfuscated C. And yes, the goal of that was to write code that was so confusing that you could not figure out what it did. Now the code could actually run and would spit out an answer, but you had to figure out what it was doing just by looking at the code. And they actually had contests to show you how confusing they could make their code, and the code could still function. So that's the thing. Think about it. Make something that no one else can understand but you, but it still actually does something. So you as a wizard programmer could make all sorts of really neat things. You were the only one who understood it, which would give you great job security, but on the other hand, for the people who were paying for this, would cause them a lot of consternation. It would also cause problems when people would leave organizations. It was really a mess, and it was starting to cost a lot of money. And it was in some ways starting to limit what we could actually build. So there was a software crisis that went on. And so a lot of people started doing a lot of research. A lot of my research back in those days was on exactly this type of stuff, in trying to figure out how to better build software-based systems. What I have in here. Back in the 80s, just to give you some size also of the scope and where we were having problems, I worked on, at the time, the largest software project in the world. It was about 4 million lines of code, and it was the biggest one at that date. And we had all sorts of people and companies in helping us manage the software. It was a real mess, because there wasn't any way of there was no known way of doing it. We were literally out in front of everybody. And we were having a real tough time. Today, just to give you a sense now that they've had better processes, better understanding, better tools, Microsoft Windows itself is over 50 million lines of code. Just the operating system, nothing else. Not Windows, not Word, not anything else. 50 million lines of code. It's staggering to think, that human beings could control that many things. Because you think about it, you have to be able to manage that. So to be able to do that successfully, you needed techniques that would help you encapsulate things and build up blocks. So think about it. Think if you were trying to build a puzzle and all the puzzle colors were all the same color, and then someone just mixed it all up and took it all apart and says, now you have to put the puzzle back together again. Well, the most you could do is that maybe you could put some of the edges together, but then the rest of it would just be a mess. When you have a puzzle that has all sorts of colors and images, one of the things that you do is you break it up into those images and pieces to help you manage it, and so you can solve the problem a little bit better. In a sense, that was kind of what we were trying to deal with, is that how do you break up this thing that looked like a big homogeneous blob into pieces that you could then manage? So that last bullet I have there, part of the solution boils down to encapsulating solutions and then providing interfaces to them. So think about it in the sense of that, if I could say I had a solution for doing this type of problem, and hang on one second, I gotta stop for a second. Okay, sorry about that, I had a phone call. I don't remember where I was at now. We were talking about encapsulation. I think. Talked about that. Oh, we didn't talk about encapsulation. We just started. Okay, so we ended up here. Okay, I just must have hit my mouse here again. Okay, so what is this magical object that we've all been alluding to? Is that it's going to solve the software crisis, which it really didn't, but it did help an awful lot. It's just like the word in life. You have a property, your name, a method. So think this is you. This is you here. So here you are as an object. Here you have a property, your color of your hair, the state of you, you're a student, your name, all those things are properties of you. And then what you do is you have a method. A method is how I talk to this object to be able to get information like properties about it. So in the old days, what would happen is that you didn't have any of these things to stop you. What you would do is you would just go and mess with the properties, or you go and grab the data wherever you wanted to. With object technology, it forces this interface on you. You have to do it this way. You have to hide the property information, and then you have to create a method that allows for access to that. So it forces this structure onto you. So let's see. So what is this thing about class? Well, let's say for you, your class is human. You are an instance of a human class. So you are this human object down here. Okay? So a class would be all human beings, which is a huge thing. And then what you have here is you have an instance, which is you. Now, humans, there's the classes that are above it, right? The classes above it would be things of like mammals, okay? Creatures on Earth, all sorts of other stuff. What these classes allow us to do, and this is something we're going to talk about later on, is that you can put classes together to create different types of objects. And it's a way of creating templates so that whenever you want to build a class of a human object, you know that you can get something with a name, something with a social security number, something with certain method calls like asking my name, asking how I feel. All those things can be put in as templates inside of a class, and so that every time you want a new object, you just say new object with whatever name. So if this was class people, and then you said I want to have a new people, a new person, I would just create this new object, and I would fill out all the information that I wanted on it, and I'd be all done. And I could build 100 of those. And I only had to write the class once, but I can create multiple objects that are specific for what I'm trying to do. And this goes, I mean, I'm talking about people, but obviously cars, think of this as an automobile, right? You have an automobile as a class, and then you create an object, and then you have, well, what make or model is it? How fast can it go? Then you have methods that say, well, how fast can the car go? Or make it a real car, make it a simulated car. And then what's in here is the size of the engine in a simulated model. So like, let's say you're playing like a game, and you said, well, I increase the speed. This algorithm in the back over here will start to increase, will go through the algorithm of if I increase the speed, the car will go faster. It'll go down the road more. And they put it all inside of these objects. Okay. So, oops, I'm terribly sorry. Maybe I should stop using the mouse. Just use this. Okay, so what is the fundamental part, though, that make those objects kind of do what we were talking about? And these are words that you probably will see in your studies. This is the part of the abstraction that makes it all work. So these are kind of like the physics, the concepts of what they use to imply into those physical implementations of objects and classes. And then one of the key ones is information hiding. And that's to protect data so that no one else but you can make those changes, or whoever you've allowed to make changes can do it. So think about it. I got a little example. You go in for a burger. You order it. It comes out from the back. You have no idea, maybe for good reason, where it came from, or what it came from. We're assuming it came from an animal that you want to eat, but or a veggie burger, which would be better. But you have no idea how the chef did it. So think of this burger joint, okay? And you walk into it, and there is just the front room, and somewhere in the back you can't see the cook. The person in the front takes an order, turns around, or puts it into a machine, sends something in the back, and then walks over, takes out a tray, and hands it to you. You have no idea what happened in the back. Okay, your restaurant's the same way. You talk to a waiter, the waiter goes off and takes your order, walks away, comes back with some food. You have no idea what happened. That is all information. You do not know the chef's secret recipes. Okay, you don't get to see any of that kind of stuff. That's the same. Keep that in mind as you're writing objects, because that is what objects are all about. Is hiding that information from users of the object that you're creating. Encapsulation. Encapsulation is putting these things all in one thing. So think of like that the kitchen where the chef is. Inside of that encapsulated object is where the chef does all their work. Inside of the ordering part of the restaurant is where you do the ordering. Okay, and the chef has no idea how ordering works, doesn't know anything about you, because all he knows is he gets requests from the person who takes the order for a burger. Knows nothing about the customer. That's all hidden from him. He knows nothing about the customer object. He knows nothing about. You know nothing about the cook. All both know about, is this one object called the order taker, for lack of a better word. All right. So encapsulation, you hide the details of what's happening in the back. And again, your appreciation for this is that in the bad old days, people used to be able to see into and change anything else in the system. There was nothing in the system that would stop them other than their own discipline not to make those changes. And unfortunately, when you don't have a computer, a compiler stopping you from do that, people will take the easier path most often. All right, so again, this is just a real quick introduction into the concept. Don't, watch it a couple of times if you have to, read some more. Don't worry about if it's all not sinking in. I do not want to stress you out. On the other hand, I really hate it when people tell me, just trust me on this and just put it down. So I wanted to give you some flavor as to what's going on and why we're going down this path and what was our motivation for doing this, and what the concept is trying to do, so that when we start showing you in the code, like when we showed you the main thing, like every object that's the start has to have one has the main. Well, that main is a method call, and that is an interface into the system that says, here's where it all starts. It's right here. This is where you're going to launch the application from, right at this location. It's a method call. Okay. Virtual machines. And actually what I have there is that let someone else do the hard part. So again, we're going to take this concept of information hiding and encapsulation, and we're going to use it even how the language itself runs. Because one of the things that we didn't really talk about a whole lot, I don't think the book does, is that what was the real special thing about Java? Well, this is it. This is where Java really makes its contribution to the world, and it's in this what's called a Java Virtual Machine, JVM, Java Virtual Machine. And the wonderful thing about what it does is that it takes your Java program, puts it through the Java compiler, and then runs it on a Java Virtual Machine that is set up for Windows, Unix, or a Macintosh. At least that's how it started. This is right here in the middle here is where things started. Before this, every program had to be built specifically for a Windows machine, a Unix machine, or a Macintosh machine. And all of these are radically different architectures. What they did by building this normalized virtual machine part here is they allowed you to write programs just to this virtual machine, and then the virtual machine itself, something you don't have to worry about. Microsoft works on this. Whoever does the one for Linux does this. The Apple will take care of this, and they will build in the part that says, okay, I'll take my underlying hardware and work with this virtual machine. I'll take my underlying hardware and work with this one. Same thing from these guys. You don't have to see this. Okay, you just see this. But what do you get out of it is you write the program once, it works on all of these different platforms. And today, it works on a lot more platforms. It's embedded into all sorts of stuff. It's in your ATM machines. It's in soda machines. It's in cash registers. It's inside of your car. It's inside of all sorts of embedded. It's inside of your phone. All of these things, this one program, the Java Virtual Machine, and you can bring it into any of these devices. Before, that was an extremely expensive, time-consuming task, and that is why right now Oracle spouts about is 3 billion devices run Java. That's extraordinary. And that is the power of Java. It's not really the objects. Java did not invent objects. That was not their main claim to fame. I mean, they've done some things and they have their own object model and they've enhanced some stuff for sure. But that was developed long before them, and we're going to talk a little bit about that, or I already did. Maybe I did that in another package. Their key part was this thing right here. This was truly amazing to be able to write a program once and have it run on several different machines. That was really cool. Okay. So, what is the process of how you get a program written? And then once you have it written, how does it run on the machine? And so I'm going to go through 2 slides that are going to kind of put the process all together. Again, you're not going to be tested on this, but I also want you to understand how the workflow is going here so that you understand what each of the tools and things you have access to contribute into what is going on. So we start here with problem needs solving. Okay, someone has a problem. They have a requirement for some type of a product. You know, right now for most of our projects, they'll be fairly simple. You know, add some numbers together, do an algorithm or something like that. Someday, you know, someone's going to give you a problem to build a system to manage a bank or to launch a rocket or something. Those are much bigger problems and have to be decomposed in a more complex manner. But for our simple problems, even for what we're doing, we need to break up the problem into a series of steps. These steps are altogether often referred to as an algorithm, depending upon if it's just one type of thing. If you're building an entire system, it's not usually called an algorithm, but for example, if you have something you're sorting, we call them sorting algorithms. But for right now, you break it up into a bunch of steps. And one of the ways you do this is all this part in here can be all done in English. In other words, these are like word problems in math, is that where you just have to take the problem apart and decompose, okay, what is it really asking for here? And then just write pseudocode, just write some make-believe, okay, in step 1 I got to do this, step 2 I got to do that, step 3. Think, for example, like ordering the burger, okay? If you had to write a program that was going to simulate ordering that burger, you'd have to say, well, the first thing you do is you find out what does the person want, and then you may say, well, gee, what do you want to have fries with that, or do you want to have a Coke with that? And then you have to take all that information, but you can write that in English for a while. You don't have to immediately start with programming. As a matter of fact, I really would like you to get into the habit of trying to do some design work on a piece of paper before you start programming, because the thought process and the skills of solving the problem is as important as the implementation in the programming language. And it's also easier that if you do it with just a simple piece of paper or a tool or whatever you're using, before you start investing in the time to make code work, design is something that you can change really quickly. It's easy to find, oh, there's an error in my thought process here. I need to make a change. Once you start to do it in code, you've now spent time writing all that code, and then you say, I just wasted a bunch of time because I got to throw it all away if you found out you made a mistake in how the problem was supposed to be done. All right, so once you've gotten a rough design together, then you can start writing a program based on what you found out from these steps. So you're going to write in Java. Java is a language much like the human language. It has a bunch of reserved words that have meaning to those that understand Java. So think of a dictionary. Dictionary is a bunch of reserved words. The dictionary for Java is much smaller, but it still has a dictionary of special words that is part of the Java language. It has a bunch of rules. Just like grammar, you can only use certain words together. If you use the words out of sequence, if you say apple, green, Charlie, Mac, and you go, what does that all mean? It makes no sense to anybody. Well, your computer is the same way. If you do not use those reserved words in the correct way that they want to be, the compiler can understand it, then it's not going to work. It has a bunch of, over time they found that some of the features not part of the reserved word set were used a lot. So what Java has done over the years, that's why you have Java, we're up to Java 10 now. We're looking at Java 8. Each of those successive years, they started out obviously with a Java 2 and a 3 and a 4, if I remember. They added some additional things. They didn't really change a lot of the reserved words. So what they did is they added some things to what we call the libraries and classes. And just like for human beings, we're going to find that there are special operations that have only meanings to them. Like in a human language, you have special terms for medicine, engineering, gaming, slang, all sorts of stuff that has only meaning to a certain type of problem. And when we find out that there is we will find that there are classes that are not part of the Java language, but they are classes that we can import and use into our program to help make our work easier. For example, Microsoft creating a window in Microsoft on a Microsoft machine or a Macintosh machine, you do not have it's not part of the language, but there are special other libraries that you can include in your program that will give you classes that you can then reuse to create a window or to create some type of graphical object on the screen. Right? There is no library in Java that necessarily is going to help you with writing over the Ethernet or over the internet or to a web page or something like that. But there are plenty of third-party classes that you can import and reuse that will do that for you. So that's where all these specialized part is. So when you're writing the program, you're using the reserved words, you're using the included classes that came with the language, and then there are going to be some ones that you're going to reuse from others, ones that you've also written that you're going to want to reuse in the language. So you can use all three of those things. Then you're going to put it through the Java compiler. So you've written your code in Eclipse, you've got a bunch of text, you're now going to say compile this thing, and then the compiler takes all those Java language instructions and says, is this language okay? Is it legal? Did you follow all the all the rules? Is everything there? If it is, then it's going to say, well, I understand it. It looks all right. I'm going to convert all of your stuff into something that you don't want to read, but it's something called bytecodes. And it's going to take those bytecodes, because it's going to convert it into whatever that Java virtual machine understands. So it's going to send it to here. And then when you try to run it, this is where the rubber hits the road. The Java virtual machine takes all those bytecodes and converts it into the machine code for that particular machine. And as we said before, it would change it to a Windows machine, a Unix, or a Macintosh. And you operate the program. Okay, so let's just look at that. There's a little bit more complexity. Now I want to start using some of the words of some of the tools that you have at your disposal for doing this. So now we saw an overarching kind of view of how a program is created, how you do some design work, how you do all this stuff, and that. But now I'm going to try to also put it into using some of the terms and some of the things that you've already seen. So again, we start here, problem needs solving. Again, we do our design work. Nothing really changes here. But now we're going to be a little bit more precise. Okay, you write a program inside of your Eclipse IDE. And then, as I told you in the other video, the compiler is always compiling. Always, every time you write something, it's trying to compile. It's trying to compile. It's looking for problems all the time. So that means you don't have to go through some kind of a compile. In the old days, you would actually have to write all the code and then go to the compiler and have it run for you. Okay, and then you would see if there was any errors then. Then you go back into an editor. Then you'd leave the editor and you go back to a compiler. Now it's all built into one thing, and it's always compiling. If you decide that everything was okay and that it compiled all right, then you can take the code and convert it into bytecode, because you're going to press like that triangle button up at the top there, that run play button. And what it's going to do is take all that bytecode and send it over to the JVM, which is inside of the Java runtime environment. So let's just step back just for a second here. I want to think about what we installed. You installed the Eclipse IDE. And then we installed something called the Java Development Environment, the JDK. And I told you inside of the JDK, you had two options. If you're a developer, you got the JDK. All right. If you are not a developer, you just get the JRE, the Java Runtime Environment, where the JVM lives. It lives inside of that. When you do the JDK, you get the JDK part, this compiler part, but you also get the JRE. It comes compiled in. That's why you don't have to do it separately. Back in the old days, you used to have to put these all in as packages. I think I told you in another video, it used to be a bit of a pain in the butt to get things to work. Now it's much easier. But anyway, so the JDK got us through here. Now we're into the JRE. Inside of the JRE, the Java Virtual Machine takes all those bytecodes, converts it into the computing machine being used, all the machine code, and that assembly language or that machine code runs on the computer. But you don't see that. That is all hidden from you. The program runs. Yay, it runs. Or is it okay? Because this is a syntax error. When you have problems over here, these are syntax errors. But then you can have logic errors, which means, yes, it ran, yay, but you didn't get the right answer. Okay, you expected something else, you didn't get the right answer. So you got to go back into the IDE and write the program again. But this is now for logic errors, not for syntax errors, which the logic errors can sometimes be much harder to figure out than syntax errors, because there's no tool here to help you with logic errors. You're the only person who can tell what my logic is wrong about. Now, down here, I included, this is that other part that we talked about. So here's all the Java reserve words. Here's the Java built-in classes with every program. Here's the Java included classes that you have to include, okay, that you built. And then classes you or others have developed get included in here. So these are all the outside packages that are part of the language that that make up this whole process. So problems, break it up into a design, write the program, the compiler, make sure the syntax is correct, converts it into bytecode when you're ready to run, turns it over to the Java virtual machine, which converts it all into the machine code or assembly language. Then you run it on the hardware, and then hopefully if you get the right answer, you're done. If you're not done, then you got to go back through the process and do it again. And these are the things that control it: the reserve word, the built-in classes, the Java included classes that you get with every hardware suite that you're dealing with, and then classes that you or others have developed that you wish to include. All of these things have to be made visible. When you're looking in the IDE, you notice how we were building with packages. Well, what we're going to see is that there's ways that you have to do things with import, and I think some of the next program examples we will start to see that word import to bring in these outside classes. Okay, so these are the Java keywords. This is it. I'm not going to go through them all, obviously, but there's not a lot, and it's not, so there's not a lot of these you're going to have to learn or anything like that. This isn't the hard part. The tricky part with being a really good programmer is learning all the different objects out there. Typically they use the word application programmer's interface, which are all those interfaces. They typically, like for example, if you're going to deal with Microsoft Windows and build a Windows system, or if you're going to get involved with trying to read data about the Windows operating system, there's something called WMI objects. That's not a test. I'm just explaining to you a different type of objects there are out there. And there's hundreds, if not thousands, of those Windows objects. Remember I told you it was 50 million lines of code are built into, is for the Windows operating system. 50 million. There's a lot of objects, and there's a lot of different services and a lot of different things. And so what it comes down to is that is you as a professional software engineer, it becomes like, well, over time you're going to learn a lot of objects, and you're going to learn a lot of ways to find this data and work with it. Actually, one of the things that I plan on doing in one of my next sets is talking about how to work with some of the documentation packages and how to find some of this data much easier. We don't need that quite yet, but somewhere down the road I'll go through some of the documentation. As a matter of fact, This here is a bit of a start. These documents here, this one here specifically, if you want to click on that and or actually you can't click on it in this pitch list thing, but if you just want to write that down, if you just look up Java documentation 8, because that's what you're mainly focused on, you should end up with some type of link like this at the Oracle site. And you'll get to see all the different classes and things that are built in or that are easily available for you to write with your programs. You either look at that and say, oh my goodness, there's too much. Again, you won't have to memorize and know all of those, but you can also think of like, these are all the really neat things I don't have to reinvent. I can just reuse them, and I can write some very powerful applications really quickly. And that's really what this was all about. That was part of getting rid of that software crisis and all that money and time, and making things simpler, was so that more people could write software quicker and very cost efficient than what they could at the time. In other words, get rid of the wizards. Just let all the rest of us be able to do some work. So anyway, that's it for this little presentation. My goal was to just give you a little bit of an overview of what I saw from Chapter 1, a little bit more on objects in Java, because I want to give you context. So maybe this is something we wouldn't have done in class, but hopefully this is something will help you. And again, I'll take any questions on this. And I do apologize again for my travel schedule. It was really not planned, and quite honestly, I'm not enjoying it too much myself. So we're both not happy. Take care. Bye-bye.